Good morning, guys, again, and hopefully the camera settings is better now. Anyway, today's lecture is all about basically chapter 15. So we're done with fluid dynamics, and we're going to move to waves. Do you guys remember chapter 14 from Physics 4A? These those who are here. Did you cover that chapter on oscillations, basically? Yes or no?
Yes.
Okay, so yeah, let's review that chapter quickly in here. Oh yeah, I can move the wire in here. Instead of being in the way, we can at least solve that issue a little bit. Anyway, so let's talk a little bit about that chapter namely 14, which is oscillations, which we did way back. And then we're going to introduce the waves and the difference between what a wave is and what an oscillation is. So since I was in the other camera already, oh man, I deleted it by mistake. Why do I get this issue in here? Okay, it's still not showing. Okay. And now the wire is hanging in here. Sorry about that. Oh man, I can't get this setting correct. Anyway, so you probably did the harmonic oscillator using a spring and mass system there. Basically what you have a spring and you have a mass in here, and the mass has it was given at that point, which is M, and the camera is, I'm sorry about these technical issues, kind of not focused. And the spring constant was K, and what you did, you applied F equals to MA, you have the restoring force in here, which is minus KX, where X is the elongation of the string. And then in here, this is basically, I'm assuming that this experiment could be conducted basically after equilibrium, because the weight, all it does in here for mg, it shifts the equilibrium position from the string being completely and stretch to a spring with a new stretch, and that stretch basically is given by mg equals to KL naught or kx naught, where x naught is the new elongation, namely the length of the string is no longer a spring is no longer L naught, but rather L naught plus x naught. And now we have a new position of equilibrium. And if we disturb this equilibrium a little bit, the spring can compress or can elongate by a new amount in addition to this equilibrium value by an amount x, and that the acceleration then is given by mx the double naught in this case, and applying F equals to ma. So that's the only restoring force in here. I cannot really draw this as a vector because of the fact that this is the acceleration, this is ma. So mx double naught is equal to minus kx. And this, of course, if I move this value to the other side, you can write it as x double naught, which is just the derivative of the position twice, namely the acceleration, is k over m times x is equal to 0. And at that point, you say, okay, I know what this is. This is actually an oscillation of angular frequency omega squared is equal to k over m. And basically what that means is that the solution of this one is some sort of a sine function. Let's say, for example, of a given amplitude, which depends on the initial disturbance in here. So an amplitude times cosine of this omega itself times the time dependency. It may be have a phase shift. You may start the clock not immediately after the disturbance happens, but later on. So you account for that by some phase shift, which you call it phi naught. A and phi naught are determined by the so-called initial conditions. Initial conditions. This is more or less basically what you guys have done, and basically what the amplitude of oscillations in this case, and the initial phase shift, which we can take it to be 0 if we choose to kick basically the clock immediately push the time basically clock immediately after the system is disturbed from its initial conditions. So this has no initial kick in it, has no initial velocity in it, and this initial phase basically has to do with that initial velocity. So if the initial velocity is 0, so the expression is just A cosine omega t, and then A is just the amplitude of the oscillations that you have seen in here. And this one will go into a sine wave behavior, which is typical of this this thing in here. So the oscillations are given by this basically function of as a time dependent. So this is the x now as a function of time. And in this case, it's some sort of a sine function. I'm doing it as a cosine. We call it sine all the time, regardless of a sine or a cosine. The period of oscillation is, in this case, if you guys remember, was t, and t is related to that quantity, omega, by this expression, where again, omega is just square root of k, which is a restoring parameter from the spring, divided by the inertia of the that is actually resisting this change in motion. And that's basically, in a nutshell, what that expression is. Does this ring a bell to some of you? Okay, so this is basically, in a nutshell, an oscillation from chapter 14. You probably did it also with another system, namely a pendulum. So basically what you do for the pendulum, you take a pendulum, which is namely a new, which is a string. This is in its equilibrium position, but you disturb it again. There is a keyword in here that seems to be following us all along, equilibrium position. If I let go of the string and the mass in here is going to sit in this position. What you do, again, you disturb it from its equilibrium position, and then you apply F equals to MA or tau equals to I alpha, whichever you like. It doesn't matter, since this is a point particle, I'm taking M in this case. I'm assuming the length of this string. This is a string, not a spring, of length t. Therefore, there is a tension in here, there is a force in here, mg, and mg acts as the restoring force. It acts just like K was in the spring. So you apply that one in here, and basically after you do all of the equations, you end up with a complicated equation, as a matter of fact, which is for a point particle, it's going to be ml squared. That's the, I'm applying tau equals to I alpha, basically, where alpha is the second derivative of theta, is the angular velocity. Okay, angular acceleration, I'm sorry, angular acceleration. Angular velocity usually is omega in this case. So ml alpha or theta double naught is equal to, the restoring force in here is going to be complicated. It's going to be actually minus mg times L times sine of theta. Okay, L and L square cancels, the m cancels from both sides, and I have this complicated equation that I'm supposed to solve, and it involves basically g over L times sine of theta. This is complicated. You cannot really solve it as is. So what you do in this case, you assume theta is not large. Theta is small in such a way that theta and sine theta are equal, where theta is measured actually in radians. You have to be very careful with this approximation. Then in this case, you resolve back to theta double naught plus g over L times theta is equal to 0. And you say then too that, hey, listen, this is actually an oscillation. As a matter of fact, that's actually how the clocks work. I mean, what is it that... the old clocks, basically, the one that they sit in the living room. So that's how, and then you can find, again, you can argue that omega squared in here, the angular velocity of oscillations, which is different than the other omega I was talking about, different than theta naught, actually. So theta will be, in this case, again, given by some amplitude, which I'm going to call theta naught in here, times a sine or a cosine, doesn't matter which one you write, because both of them are the same, times some, in this case, it's going to be square root of g over L times t plus some initial phase, okay? And this phase has nothing to do with the initial displacement in here. This is the phase with which this one is oscillating, and has to do more with the clock than anything else. And again, with the judicial choosing of the time, the initial time, if you release this one from rest, so the initial velocity is equal to 0. So in this case, what you say at t equal to 0, of course. So in this case, theta naught, phi naught will be 0, and the solution will be simply the initial amplitude with which you released your pendulum times cosine of this omega. And I'm careful in here not to use the word omega in this case because there is some confusion at times between which omega you're meaning. There is the actual omega, which is the angular velocity with which this one is going back and forth, and there is the theta naught, which is the derivative of this expression in here. So this one has to do with the period, which is again given by 2 pi over omega, which is namely square root of L over G. Just flip that square root and you're fine. So again, this is stuff that you guys have seen from chapter 14, namely oscillations. Okay, and oscillations, they have a key component in them. They're known as local disturbances. What I mean by disturbance, in the first case of the spring was relaxed at equilibrium. So if I take, for example, the example of a spring and a mass attached to it, and the spring actually can be taken at L naught in this case because there is no initial displacement to it. And then this is equilibrium. So this has a mass m, this is spring constant k. And then what I do in this case, I come and cause trouble, disturb the system from its equilibrium. So give it an initial displacement, elongation in this case x naught, or compression, doesn't matter which one you do, one or the other, or give it a kick, an initial velocity, or a kick this way, an initial velocity. One or a combination of the above will cause the system to go out of equilibrium. It's no longer in equilibrium, it's disturbed. But this disturbance now, it's local, meaning it doesn't travel in space, it doesn't go anywhere. It stays in this region only. It doesn't go far from this place. So that is what an oscillation is. So it's a local disturbance. And the case of the spring, I mean, the other spring, the one that is attached to the ceiling, for example, and you put a mass. Before you put the mass, the length was L naught. Now, when you add a mass to it, immediately the spring will stretch by an amount x naught. That depends on this mass. As a matter of fact, x naught is equal to mg divided by k, where k is the spring constant. But then after that, that's the initial, that's now the equilibrium position. So what you do again, you go and come in here and cause trouble, namely disturb the system out of its equilibrium. You push it up or you push it down, doesn't matter which way. Then the system, either you give it an initial displacement or you give it an initial velocity. What I mean by initial displacement in this case is compression or elongation of the spring. And in either case, the spring starts to oscillate at that point. So this again is local. In the case of the pendulum, it's the same thing. The pendulum would want to stay like this. So if you leave it like that, it's going to stay forever and ever and ever. There is no problem with it. But again, you cause trouble again by just disturbing out of its equilibrium, either by moving the mass, that's one way or the other. It doesn't matter what you do, either by an initial displacement that is counterclockwise, namely the angle is positive, or clockwise, namely the angle is positive, or you give it a kick in the counterclock position, basically give it an initial velocity that is positive. The system starts to oscillate then, or you kick it in the other side, doesn't matter, or a combination of all, okay? Combination of these conditions that will cause the system to go out of equilibrium and starts to oscillate. So that is what an oscillation is. The wave, though, is slightly different than that. The wave is actually, a system, first of all, is calm. For example, if you go to the surface of the water and you look at it when there is no wind blowing or anything like that, it's calm. But you throw a rock in it, now it's no longer calm. It's disturbed. So what you do in this case, you come to this point in here in the water and you throw a rock in here, and this rock will create a disturbance in this region only of the water. But what you notice is this disturbance does not stay there, it moves. As a matter of fact, it moves in every single direction in what is actually circular, what we call a wave now. So this disturbance now travels. So they are no longer local disturbances, but traveling, or a disturbance that travels. disturbance that travels. That is the key difference between the two phenomena. Okay, the key thing between the two phenomena is that one of them is localized and the other one is traveling. So let me switch to my other screen, share with you the screen in here. Hold on. Where is my Zoom session? And then share screen. So that's item one of the discussion, is to list the difference between the two, between an oscillation and a wave. So the oscillation is a localized disturbance, whereas the wave is a traveling disturbance from equilibrium. So you're asking me for a disturbance from where? The system was calm, in this case, was not disturbed. Now it has been disturbed. This disturbance travel in space. Another example, for example, is the air. The air is calm, and the pressure is uniform in the air, and the density in the air is uniform, but somebody speaks, okay, talks, like the way I'm doing right now. So what they do in this case, immediately in the vicinity of their basically space, immediately in their mouth, they have created disturbance because they have disturbed that pressure and that density in the air. And now that disturbance doesn't stay in that point. It's going to travel, okay? It's going to travel in actually spherical, in spheres, not in a circle. In the case of the water, it's going to be on a circular pattern, okay? Characterized by what is known as wavefronts, similar to this one in here, because when I drew this one earlier, if you guys remember, has this shape. So the amplitude of the oscillation sometimes is max, sometimes is min, because it's a sine wave. This one also is similar. The amplitude of the disturbance at points in here is going to be high, which is a crest, and sometimes it's low, which is a trough, and then those crests and troughs, they will travel in space. So it's exactly similar to this situation in here, okay? And this is in the case of the surface water. In the case of sound, what happened in this case, the air will come with two different kinds of air, basically structures. At some point, the air is compressed, and at some other regions, the air is actually relaxed, and then followed by regions of compression, and followed of the regions which call them rarefications, similar to this point in here, similar to this point in here. So the air now is less, and the air is more concentrated in some regions. So this is compressed air, and this is rarefied air. So that's similar in a sense, and then when it reaches the ear of the person who's receiving this disturbance, basically the ear drum itself is yanked in and out of its equilibrium position and becomes an oscillation again for the ear, because the ear now is being basically pushed by compressional side of the wave and actually yanked out of its place back by the rarefied region. And these oscillations go and become basically, the ear basically interpreted as some sort of an electrical signal, sends it to the brain, and the brain gives it some specific meaning that the person can at the end make sense of sound if it's has some sort of harmonics. If it's completely out of those harmonic regions, then it becomes just like noise. Does this make sense to you guys, at least this general description? Yes, no, or maybe?
Yes.
Okay. Yeah, the item that I want you to really, the first one that I want you guys to address is the difference between an oscillation and a wave. Put it in your own terms, okay? Put it in your own words. The key difference, though, is one of them stays in its place, does not move. The other one actually changes places from place to place to place and travels in space, actually. What that translates mathematically, though, into the following situation. One of them, I can describe it as a function of time only. And the other one has to be a function of both space and time. Can you guess which one is oscillation and which one is a wave from these two? Option 1 or option 2? Which one is an oscillation, do you think?
I say the oscillation is number 2.
Is that this?
I say it's number 1.
Say it's number 1.
Yeah, because this one only changes with time, so it doesn't move in space. This one moves in space. Do you agree now?
I'm sorry, I got oscillation and wave definition confused.
Okay, yeah, that's fine. You don't have to apologize. I mean, sometimes we have. So this one is actually localized because it's happening only in one point in space. There is no spatial parameter in it. There is no X in it. This one, though, depends also on where you are. It does not depend just on the time. It's not like bobbing up and down. I mean, if you go on the surface of the water and you're on a boat, for example, for you, you only feel this because you are located in a specific point in space. In space, so for you, the boat will go up and down, up and down. When the wave comes in, the next wave front, it pushes you up, the next trough will push you down. And then for you, you're going up and down. So for you, it's actually localized behavior, although it's a wave that is causing that oscillation. But for you, you're oscillating. But if you look at it from the big picture, for example, for somebody standing in the shoreline, they will see this waves, one coming after the other. They will see a big high wave followed by the water going receding into the beach and then coming back again toward them and going back. So they see actually the full-fledged picture, okay? So this one, as a matter of fact, what you can do, you can take a camera and take a picture of it. You take a camera. What you do with the camera, you freeze time. So when you freeze time, you're looking at how the wave looks like in space. So you can take that picture and share it. Look at it. Look how it's distributed and throughout the ocean. So you can just share that one and then do the opposite of this one. Instead of fixing it in space like this one, like you're sitting on a boat, you can actually use a camera and you freeze its behavior in time. So that is actually a wave. So this is a wave because it travels from place to place. Because it has X in it. I mean, I'm taking the simple case where we're only dealing with an X and T, because the more complicated the case is going to be a nightmare, okay? I know some of you are sitting in my Physics 4B, and at some point toward the end of Physics 4B, we're going to be dealing with something as complicated as that, albeit we're going to try to simplify it still, okay? Because that's the electromagnetic waves, which is another thing. So that's basically we're not going to be dealing in this course with the non-mechanical waves. We're going to be dealing just with mechanical waves. But for those sitting in physical 4B, they will be dealing actually with the EM waves, which is a different kind of waves. Okay. So for this one, when I say mechanical waves, all I need is F equals to MA. That's what mechanics reside on. Okay. So that's what we're going to do to describe this wave. So the ultimate goal is to study this one. So here is the problem now. Here is where the issue is going to be. This is a multivariable function. Yes or no?
Yes.
Yep.
So if you guys are not comfortable with that, I'm sorry to say that, but that's basically the thing with it in here. So that's the beast that we're going to be dealing with. So let me share with you another screen. Let me stop sharing this screen with you guys. I'm still in that one. You know what? Probably I will. What is the other camera if I can get back to it? Okay, where is the other camera? There. Okay, so I'm going to share with you another screen in here where I combined a lot of simulations. If you look at the book of Feynman, which I really recommend for you guys to look at it, it's had 3 volumes, and it's actually one of my resources in this class, in all of my classes actually. It's going to be on volume 1, chapter 47. You can go there and learn about waves and see how difficult it was in the past trying to explain how waves are. There are two types of waves that we're going to look at them. There is wave that travels to the left and wave that travels to the right. With nowadays, with the advent of computers, there are all kinds of ways of visualizing this, and you can clearly see it traveling to the left and one of them traveling to the right. There is no distinction between it. However, the functional, how the function depends basically on X and T, you can argue with it too. I mean, following that chapter 47 from the book from Feynman, which is toward the end of actually volume 1, you will see you'll appreciate actually, he will explain it and he will draw it, and then he will draw, and Feynman is not an easy person, by the way. He won Nobel Prize and he did so many things in physics. He's probably the best teacher of physics that ever existed. But the point being in here is it's really hard to do this explanation without, at least in those days, without computers. But now we have computers, so we're going to take advantage of those. Okay, does this sound like it's a good plan? Sorry, Feynman. So I created GeoGebra in here. Okay. Oh,
Sounds good.
Open so many GeoGebras, okay? Let me go back into and share with you that screen in here. Share this one. Okay. It has a bunch of basically I'm looking at the algebra in here, part of it, and I'm looking at the graphing part of it in here. What you see in here is, first of all, these are sliders for me to help me. I call time t equal to 0 all the way to 20 seconds. And v is actually the velocity in here of the wave, because I expect this wave to be traveling. This is a wave, okay? It's actually the Gaussian distribution, except it's not really a normalized Gaussian distribution, if you guys are familiar with that function. It's the exponential of negative x minus vt squared, okay? Are you guys looking at my GeoGebra animation or not?
Yeah.
Yep.
So if I let fly of time, you will see that because it has a minus here, this minus, okay, is going to move to the right, meaning toward the x positives. So if I let go of the time, so it's clearly this is traveling to the right, okay? So that's basically what this thing is. And it's traveling with the velocity v, because, let me stop the animation quickly, move back the time to 0, and change the velocity now to a higher velocity. You should see it. Of course, the simulation in here does not really, sometimes it factors in the time to slow things down, but you should see it travel faster. So it's v that is controlling how fast it's going to move, and it has already gone out of screen because the velocity is so high in this case, 5 basically, times the initial value, okay? So that is basically the so-called a right traveling. It's traveling to my right. I don't know how you see it in your screen, but this is a right wave traveling to the right. Do you guys see it on your screen also going to the right?
Yeah.
Yes.
Yep.
When you see the minus in here, between the x and the t, and the parameter v here, ignore it, just for the velocity, how fast this thing is going to move, is going to move to the right. Let me take another example, which is this one has the plus in it, okay? This, if I change time, right now, with this Gaussian distribution, if you look at it, it's 0 almost everywhere with the exception near the center, near x equals to 0, because this point is 0. So when time starts to change, it's going to shift the peak toward the left. So this wave appears to be moving, this disturbance appears to be moving to the left. So again, if I start the animation, it's clearly moving to the left. So that's basically something that with the plus, it's moving to the left. With the minus, it's moving to the right. Just to put them together, they're superimposed. The only way you see the green is because the green is last. So it covers basically the red, but if I let go of the time, you should see them, one going to the left and one going to the right. As predicted, the minus is going to the right and the positive is going to the left. If I add to them this one in here, to the mixed, okay, and let me remove the green one in here, because both of these two are moving to the right, okay, both of them have minus, but this one, the blue one, which is the last one in here, will be traveling faster. As a matter of fact, twice as fast. And that is because this one is going to 2v, whereas this one is going to V. It doesn't matter what the value of V is. At this point, it's 1. So if I double the value of V, if I can double the value of V, okay? Now the first one is moving at 2. Let's call it, if this is meter and this is second, 2 meters per second. And this one is going to be moving with 4 meters per second. So I expect the blue one to lead the red one. So let's look at it. Does this make sense to you guys?
Yeah.
Okay, so it all has to do with the combination of how X and T are combined. And I remember when I said in the beginning that this function depends both on X and T, and sure enough, it does. In this case, as a matter of fact, we're going to see that it depends on X and T in this specific fashion. X plus or minus V, which is a constant, any constant, which is the speed of the wave, as it turns out, times the time T, okay? Waves do interact, okay? Here, I have 2 waves. One with a positive value, positive amplitude. So in other words, take a string, for example, and push it up. So that has created a disturbance in the positive direction. Or if you yank it down, that has created a disturbance in the low direction, in the negative direction. So when the waves, they meet, they will cancel each other in this case. They will disappear. Okay, something particles do not. So if you have a particle 1 and particle 2, and when they meet, they smash to one another, but they cannot cancel. They stay completely distinguishable particles. They can collide and leave, but these guys, when they collide, they disappear. So for that, I'm going to go back into a time and 0 in here. So this is when they started. Actually, I started with this one negative and that one positive. So watch them when they meet, okay? I'm going to stop time in here. See, they continue in where they came from. The one that was traveling to the right was localized at in the position of -7. So this one is traveling to the right, actually. And this one is traveling to the left with a position it's located as, when the whole quantity is equal to 0, at +7. So this is +7, this is -7. And if I watch them, let me take the time slowly, okay? So as they start to merge, in this case, they cancel one another. So this is an example of what is called as destructive interference. At this instant, 3.5, I look at the string, I see it completely straight, as if nothing is in there. But the 2 waves are still completely there, but they exhibit this phenomenon. There are points in space on time where I can see the waves, and points in space where the waves seem to have disappeared. Now they emerge again and continue in their travel in the direction that they're supposed to be moving. Okay, that is destructive interference. Another kind of wave in here is this too. Both disturbances on the 2 sides of the string, if you wish, are created in the same direction, both in the up direction, for example. When they meet in here, I expect this one of amplitude 5 and the other one of amplitude 5. When they meet, they're going to be at amplitude 10. So this will be constructive interference because they're in phase. Whereas this two, clearly they're out of phase, okay? And the phase in here is expressed by this amplitude, which is the negative in here. Well, here is going to be a positive, so this is constructive interference. So again, if I let go of the time, you will see that at that point, and they continue afterwards, so they merge from it. So as if you have basically a sphere and a sphere, 2 particles, and when they collide, they become a bigger sphere, which particles do not do that, okay? Particles, when they collide, you can clearly see where the one ends and the other one starts. Whereas this one in here, they become a big thing in here, the one and the same. So if I move my time scale to about 3.5, that is where the interference is happening. That is actually where the construction is happening. So this is called the constructive interference, okay? So this is, again, something that waves exhibit, and only waves. So if you see something with specific structure in it that has interference in it, this is called interference, basically, patterns. With constructive and destructive patterns, you're dealing with a wave. This is the signature of the wave, okay? So waves have a specific signature that makes them different from particles. And this is their signature. They exhibit interference, and interference, I mean, if you throw 2 rocks on the surface of the water, you will see the wave patterns form, okay? Points where the trough seems to be higher than even a single one. So you have a circle in here and a circle in here. When they meet, the two troughs seems to be bigger. And where the, I'm sorry, and then where the, not the trough, the crests higher. And when where the trough and the crest meet, the water cancels. And you will have clear distinction picture that you're dealing with interference. So if somebody shows you that picture, you tell them, hey, this is a wave. Actually, I have two waves that combined and give me this beautiful pattern of interference. So that is item 2 of the discussion. Interference is a signature of waves. The reason why I'm saying that is down the road, we'll be doing optics. And the first assumption we're going to make is we're going to think of, I know probably that, hey, first of all, we're going to assume that light is some sort of particles, and we have a beautiful description. It's going to work fine until Mr. Young did his experiments. And when Mr. Young did his experiment, he showed actually that light interferes with this same behavior. There are points in light that are brighter than anything else, which are called bright fringes, and there are points in space that completely cancel completely. They go away completely. They're dark fringes. So that's how he concluded, way before Maxwell's equations, that light is actually a wave. We didn't know what was waving, but we knew it was wave because of this behavior, because we know that light was signing itself that it's wave. Does this make sense?
Yeah.
Yeah.
I'm going to push one a little because I'm feeling kind of great about this thing in here, okay? In the 1920s, there was an experiment actually on particles, namely electrons, and electrons exhibited this behavior too. So an electron and an electron, when you merge them, they seem to show interference also. In other words, constructive interference and destructive interference, bright fringes and dark fringes, which led Louis de Broglie immediately suggest that an electron is not actually a particle, but rather is a wave. Yet there were some experiments that show actually that an electron was a particle and not a wave. Hence the double duality of electrons and even protons and all particles that they exhibit that. And that was the birth of quantum mechanics. That's how quantum mechanics basically emerged, that particles, they do both. Because they sign like this with constructive and destructive interference, but they also do keep their, in other experiments, their basically personality is basically intact. They behave like particles. So item 2 of the discussion is wave interference, or the interference is a signature of waves. That means you're dealing with a wave. At least that's the understanding that we learn from this one in here, and it's true all the time. Okay? Let me give you some more on the oscillations that you saw in chapter 14, okay? So this is an example of an oscillation, a particle that, this is, think of it as a mass that is attached to a spring. I didn't attach it to a spring, but that's basically the point I was illustrating earlier, that this is an oscillation, okay? It's localized, and like the wave, which tend to travel in space, this one stays in its place going up and down, and so on and so forth. Okay. There is another one that I illustrated. I worked on this one last night trying to see if I can get this this thing in here. So where is my segment in here? So think of this one as some sort of a mass attached to a spring. And let me slow down the velocity a little bit back to at least get something that I can see. And even the radius in here, make it smaller. So again, this is a mass and spring system attached. This is an oscillation, typical of the stuff that is localized, okay? Don't tell me that it's changing its position, X and Y position, but this is between these two values only. It's not traveling to the other end, for example, of the other one. Here is another key difference in here, okay? And first of all, before that key difference, there is a similarity. Both of them, their oscillations are governed by restoring force and some sort of inertia, all of them. The water, the reason why it's going up and down in here, it's because of the tension, the surface tension in the water. That is actually what causing the water to oscillate up and down. And how fast it goes up and down, actually depending on the density of the water itself, the density of the medium. Same thing with the speed of sound too, and we will see that next chapter. It's actually related immediately to the properties, namely the density of the water, the density of the air, and the temperature of the air. So that actually will create tension also in the molecules and allow them to communicate with one another and basically transmit sound. So all of them have this behavior. And it's true also for the mass spring system, where it's square root of K over M. K is actually the spring constant and M is the mass. In the case of the pendulum, is square root of G over L, where G is actually the gravity, which is causing the whole oscillation. That is actually your restoring force, and L actually is the medium, which is a string in this case. If you cut it, you don't have any oscillations anymore. So that is really a common thread between waves and oscillations. They have this thing in here. Their oscillations are characterized by some sort of a restoring force, spring, gravity, tension, surface tension for the water, which is the van der Waals forces and things like that, and the inertia of the medium, okay? This last analogy, which is common thread with all of waves, created trouble so much toward the end of the 19th century, that caused so much problem for light, because again, that's a non-mechanical wave. We're going to leave that discussion toward chapter 32 for those who are sitting in physics 4B, okay? Also, the same thing is true actually for gravity waves. That's something that is actually probably discussed in physics 4D or something like that. Anyway, that is a common thread between them. What is different though is waves require a medium where they travel. This one does not require. They could do this experiment in vacuum if you like. This pendulum would oscillate, okay? Because it's not traveling in any medium, whereas surface waves, for example, for the water, need the water to travel in it. Once they reach land, there is no need for them. There is no surface tension. They don't travel, pass beyond the shoreline. Sound needs air for it to travel, okay? Basically, all mechanical waves require a medium. So that is actually something that is required for waves. Whereas, because again, it travels where? That's the stuff that is common in here. Let me take another one that is actually unique to waves, and that is the beats. Okay, we're going to see this one. I'm going to zoom out a little bit. Okay, we're going to. So this is a picture of a wave, so we don't really need to have it oscillating. So this is a picture in space, okay, of a wave, okay? What I have two waves. Think of t equal to 0. I took a picture at time t equal to 0, okay? That's all I did. It's the same wave as before, except that I did it at specific instant in time, okay? By the way, beats are not just for waves. They're actually for oscillations too, okay? Because that's what an oscillation is. It's a wave that is localized. So if I take this one in here and change the difference between these two phases, this is cosine of x, this is cosine of, why did I put v in here? I don't really need a v, so I'm glad v is 1, so otherwise it's going to cause trouble, okay? So anyway, if I change the value in here of this difference, del of omega, this is the difference between the two omegas. Technically, I should really put v then in here to make this two make sense, okay? Anyway, so this is the omega is, or the difference is, in phase is v. This is v plus some fraction of it, okay? Some small number in here, which is ranges in my simulation from 0.01 all the way to 2, okay? So it can be big, because remember, v is 1. So this difference can be big. At this point, it's practically 0. So what you see in this case is this behavior. So if I'm going to change this one in here, look at the behavior in here. So for small values, I see now I have a clear, it's oscillating still, but now between this point and this point, I actually have what looks like also another wave, okay? So I have a big wave with a very big period in this case. This is the period actually, or at least half a period, because I need two of this to make a period. So this is from here to the other side, so I can zoom out a little to see what I'm talking about in here. So from this point all the way to this point is a period, is a wave, is going like this, okay? Albeit this is not exactly what it should be because it's the same pattern. It looks like it has, it has a node in here and a node in here, and it has a maximum in here and a minimum in here. So it looks like this is how it looks like. This is one wave. But you also look at these waves too. From here to here, it's actually a period too. So there are two distinct periods in here that I can see. Whereas if this quantity is as small as possible, I can't see that, okay? So now if I increase this value, instead of just being intermediate value, the bigger period starts to become closer and closer together until now I lose any kind of personality. Now I really don't know what I have. You guys see that? I lost my big wave and I lost the small wave, and this is kind of an onset of chaos actually. This is this behavior when something starts to become chaotic. All I have is actually two waves in here, and it looks like I lost order in here. So if I have three of this, it's going to be a nightmare trying to keep that, okay? This is actually the start of a new branch of actually mathematical physics, but actually it has a lot of applications in physics too, and that is the theory of chaos that you guys heard of it. And this is the so-called basically now opening to other phenomena, okay? Like weather phenomena, for example, and turbulent behavior and things like that. But before we go that, in here at this point, we have what we call beats. This is beats, okay? So if you have two waves, for example, you have a piano that is tuned to the note, I don't know, the, what is it? The D note, okay, for example, okay? And you bring a tuning fork, and I used to have a tuning fork in here, and I don't know where to put it. You bring a tuning fork that is actually also with the same frequency, the D note also. Okay? You know specifically that frequency of the tuning fork. So you kick the tuning fork, and at the same time you hit the note in the same time, both of them. For a trained ear, you hear a hum. You hear this hum, actually. You hear this one, the big one. You will hear the notes in here. This is what a note is supposed to sound, okay? But there is a hum in it, okay? So what you do, you adjust the tension of the piano, because you know the frequency of the tuning fork. It has to be a D note, which is supposed to be this 620 hertz, for example. It has to be this specific frequency, okay? But now your ear is receiving both frequencies, adding them together per this equation. And the reason why it's adding them with no time in there, because they arrive in the same time, so the time doesn't matter. So all that matters is in there where they came from. What? I'm sorry. No. I'm sorry. The other way around. Your ear is actually in one location. So the X in here represents time, okay? So one of them is coming slightly off of the other one. You put them next to one another if you want to, okay, to eliminate any kind of problems. So in this case, one of them is coming with a frequency, let's say omega, the other one is coming with a slightly higher frequency that is not correct. So at that tension, remember, the restoring force, or omega, is in general related to the restoring force, which is going to be the tension. We're going to go through all of this stuff together, and the medium, okay? So what you do in this case, you go to the tensioner inside the piano and you adjust it. And you adjust it to bring this del as small as possible until it's practically gone, and your ear will receive both notes in the same time, beautifully in sync, and you know that you have fixed that piano. You keep on adjusting until basically that's what your ear will listen, will hear, and for the most part, it's gonna hear that hum coming very, very long time. I didn't put it 0 exactly, so if I put this one and make it 0, starting from 0 and adjust it to 0, then in this case, your ear will not really see anything in here. We'll see just the note coming from both the piano, which you're supposed to adjust, and also from the tuning fork. So this is actually has applications in there, and this is one of them for piano tuning. I met a guy who actually did this for a living. So for you, You're going to listen there and you're going to lose that hum completely. You're going to listen to it and it sounds beautifully. So this is basically in a nutshell what mechanical waves are. Actually, this is also Beats' behavior that is common to all waves, okay? Does this sound promising? What is my share screen?
Yeah.
Okay. So let's get into the math a little bit and see how this looks like. Share now this screen. So if you're not too familiar with multivariable functions, bear with me. The only thing have you guys seen this symbol before? It looks like this. Partial. Yes or no?
This is
Sorry, Lawrence, you see it before?
no, not really.
Okay. When we have a single variable function like f of x or f of t or something like that, and if I want to find the derivative of that function, usually I take its derivative and I say the derivative of the function is represented by this symbol. What I really mean by it is the following. I mean the limit of this function, of this ratio, I'm sorry, of the change in the function itself over the change in the independent variable, in this case t, when that goes to 0. When the independent variable, the change in the independent variable goes to 0. This is calculus. Does this ring a bell to you guys?
Yeah.
Yeah.
Yeah. So in this case, what I'm going to say in here is, because the function doesn't depend on one variable, it depends on actually on two variables now, okay? So when I'm doing this prime in here, I have a problem. With respect to what? You guys understand? I need to know which one I'm talking about. So in calculus, we solve that by saying, look, these two are both independent variables, by the way. X and t are independent. Variables. Okay? So I'm going to say this function at a later position in space, keep the time the same if you like, minus this function earlier, divided by the change in position. The limit of this is actually the same thing as before, except I have to be careful in here. I'm saying the derivative fix t. It's independent of x anyway, so fix t. We don't care for it. Just change x in here. Do you guys see that? So this is what I call the derivative of f with respect to x. Except in here, just to make sure that I know what I'm talking about instead of using this symbol. This is, by the way, a symbol, not a real thing, okay? So don't confuse this one. This is the actual deal, okay? This is what you do in actuality. If you're doing physics and you're trying to find the derivative of something, you actually have to do two measurements in two different instances and find their ratios and take that ratio as being the rate at which that function is changing with the independent variable. Now, if you really want to find the instantaneous values, you have to do the two measurements immediately, one after the other. And you're wondering now, how close do I need to be? That is a problem in experimentation in here that you have to resolve. Calculus gives you a symbolic representation of that operation, which is here. Okay? This is a symbol. There is nothing magical or something intrinsic in that representation. You guys understand that? So this is what I really want you to take from this. And I know your calc instructor, later on when they introduce this parameter, when you do it in calculus, they will probably have a better explanation than this and a better representation than this. But they will also, so what they say in this case is that this symbol in here indicates that this f depends on two things, two or more things, as a matter of fact, if you have three of them. So this is just a symbol now. Again, it's just like the other symbol. Just to make a distinction between the two. This is a single variable. It's clear. We know it depends on only one variable. This one is just on two or more. That's all. But this is the actual operation. So the limit of this expression when delta x goes to 0. And this is another secret also your calculus instructor will tell you, that this is the fluke. This is not real. There is no function in the world that depends on a single variable. I mean, look at the temperature. It depends on location. It depends on pressure. It depends on so many things in here. So in reality, everything that you deal with depends on so many things around you. It doesn't depend on only one parameter. So what you do in physics, actually, you try to isolate everything else and just deal with one variable at a time, okay? Keeping in mind that the reality is usually like this. So this is more real than the other one. Unfortunately, because we're dealing with waves, we're dealing with something more realistic than that, for example, you drop a mass from a height and then it's going to be 1/2 of gt squared times plus some initial velocity times t. And even in that condition, it depends probably on the air, wind, it depends on other parameters that you're neglecting in this case. So you neglect so many of them and you come up with that simple function. But in general, it's like this one. I know this is not calculus, and I don't expect to really be in control 100% of this one, but I hope that you guys have a rough idea of how this looks like. Let's give an example in here so that we can do something with it later on. Let's say, for example, f of xt is x squared sine of t, okay? This is an example. This is not a, you can come up with your own examples if you like. So what I mean by df with respect to x in this case is, it's ignored. This is constant. This is like 12 or 17 or 23, just a number. So that means the derivative of x squared. What is the derivative of x squared?
2x.
So this is simply 2x sine of t, because just like another number, that's all. I could have 5 in here, and this number all of a sudden becomes 10. So 10 times sine of t times x. So this is the normal stuff. Now, if I want to find, though, df with respect to t, this will become a number. Because treat the other one as constant. That's what this thing is saying. Treat the other variable as if it did not change. That's what that expression means. So x is not changing now. T is. So what is the derivative of a sine?
Cosine.
So this is 5x squared cosine of t. Now, hopefully with this example, there is no mystery in that curly thing in here. It's called partial, actually. Yes? Does this example bring the point closer to you guys?
I believe so.
Okay, as long as we have that in mind, because we're trying to do something real in here. So this is the two functions that we saw earlier are of this nature. First of all, I'm going to call the function f of this variable, x minus vt, exactly how I drew them earlier in the GeoGebra, okay? Where I'm going to assume that this function depends only on this combination of x and t, meaning u is equal to x minus vt. So on one side, I have a multivariable because it depends on x and t. And the other side, I have actually a single variable depending only on u, where u hides that, that double dependency on the two independent variables. So this is just math now. Because you saw, this is the right wave, by the way. The right traveling wave, okay? I'm going to call it R wave for the simplification. If you're curious about the other one, G times X, I mean, as a function of X plus VT, which I'm going to write it as G of W, where my W is going to be X plus VT. So this is going to be an L wave. Okay? So in other words, I can still hide my multivariable function inside a single variable. You guys see that? So that's the trick. So, do you guys understand? So, because all of the examples that you saw them earlier has either an x minus vt in it or an x plus vt in it, or both. I mean, it has two independent functions, one of them clearly x minus vt and the other one x plus vt, and they were moving one way or the other, okay? So one of them is going to the right and the other one going to the left. So what I'm saying in here is that the R wave is going to represent it by an f of u. Sorry, did not mean that. F of u, okay, where sorry, and The other one is, this is not my notation, by the way. This is in every single place, okay? I'm sorry about that. Hopefully you guys are in a good mood too. You're not. Sorry. F of U. Okay. So this is a textbook notation. By the way, this is actually what you find in Feynman. Okay, so let's focus on this one. There's serious stuff in here. So I need to know the derivative of f with respect to x. Again, that's the partials. That's going to be the derivative of f with respect to u times the derivative of u with respect to x. The reason why I do partials in here because u depends on x and t. So I have to have a partial in here. The reason why I do a straight derivative in here is because f is just a single variable of u. Okay. So in this case, d of u, the partial of u with respect to x is just 1. You guys see that? The partial of u with respect to x is 1, and the partial of u with respect to t is minus v. In the same token, the partial of w with respect to x is 1, and the partial of w with respect to t is positive v. This is just straight out from here. Is this correct? Because v is constant. V was just something that I artificially put in there to make the units correct. Does this make sense?
Yeah, it's getting clear.
Okay, so this then, the partial of u with respect to x is simply the partial, the straight derivative, the old one that you guys have seen with respect to u, because this is 1. Okay. So empowered with that, I'm going to look at the second derivative of f with respect to x. I'm going to use the chain rule one more time, which is the derivative with respect to x of the derivative of f with respect to u. And that is the derivative of, sorry, Control Z, the derivative with respect to u of this derivative of f with respect to u. I'm sorry, why did I put here? This is x, times the derivative of u with respect to x. I'm trying to apply the chain rule in here. I hope you guys remember that. This is 1, and this is actually df with respect to u from the previous argument, and this will become the derivative of, with respect to u, of the derivative of f with respect to u, which is just the second derivative of f with respect to u. So this will simply become the partial derivative of f, the second one, with respect to x, is simply the derivative of f with respect to u. This is the result number 1 that I will need later on, okay? So we're going to arrive at something similar, because remember, in the previous examples that I started with, they all had this form, x double naught, the second derivative with respect to time, plus some constant, which later on I called omega squared, times x is equal to 0. That was the oscillation equation. My goal now is to find a wave equation, okay? I want to know how these derivatives are connected to one another so that if next time I see it, I recognize it. I know exactly what I'm dealing with. I deal with the wave then. Just like as much as I recognize that equation, when I apply F equals to MA, I know exactly that I'm dealing with an oscillation. This is the same token. This is the same level of reasoning that we're going to do now. But this relates a derivative of f with respect to x with something that is u. And u was not really part of the initial problem. What we had is x and t. So I better find the derivative of f with respect to t now and see how that works for me, because we found the derivative with respect to x. So what I'm going to say in here is the derivative of f with respect to t is the derivative of f with respect to u times the derivative of derivative of u, I'm playing the chain rule again, with respect to t. This is equal to minus v. This is minus v. So this is minus v, the derivative of f with respect to u. I'm going to take the derivative one more time. So the derivative of f with respect to t is going to be equal to the derivative with respect to t of the derivative of f with respect to t. This, I know the answer to it already. It's minus v, the derivative of f with respect to u. But I need to do the chain rule for the outer derivative, which gives me the derivative with respect to u of this derivative with respect to t times the derivative of u with respect to t. And this is another minus v, the same thing. And this one is a minus v, the derivative of f with respect to u. So I have a minus times minus, that's a plus. And now the second equation for the second derivative with respect to time is going to have a positive v squared. Now the derivative of f with respect to u. That is the second equation. Okay, equation 2 and equation 1, the derivative of f with respect to u, the second one is the same thing as the partial with respect to x. So what this equation then says is the following. If I ever encounter this situation where the second derivative of f with respect to t is some number positive times the second derivative of f with respect to t, I'm sorry, with respect to x. Because this term, the derivative with respect to u, the second derivative with respect to u, is the same thing as the second derivative, as the partial second derivative with respect to x per equation 1. So I'm subbing in here by that. So this is the equation I'm looking for. So this is what I want, the wave equation. Okay, so the wave equation, if I put it in the same side as the oscillation equation, looks like this. Now I have two variables. That's why I'm dealing with these partials everywhere. So the second derivative of any function with respect to t, just like this one, minus, not plus, minus some constant positive. Here it was a positive plus constant positive. But now the second derivative of f with respect to the position is equal to 0. What I'm dealing with in here, I'm dealing with a wave. So this is my wave equation. Okay. I argued this for f of u, but you could have done it for g of w in the same argument. The only thing in here is this will pick up a positive v, and the second one will pick up a positive v, and a positive v times a positive v is going to be positive v squared. So it's going to be the same thing. It's going to be identical, with the exception that the left and the right, so instead of having a minus v squared, basically the minus squared, it becomes a positive. You're going to have a minus times a positive squared, which is going to stay positive anyway. So in general, the wave equation is of this form. Where y represents, in this case, any kind of wave traveling to the left or the right, it doesn't matter. So that is in your textbook. As a matter of fact, the book has a full derivation for it too. So don't blame me that I used multivariables for you guys and I have partials in here. This is actually in this chapter. So this is not something that is completely out of the realm of, the only thing in there is they do it for the harmonic waves, and it is for the general case. It doesn't matter harmonic or non-harmonic. Just to show you, this is on page 473, equation 1512 in your textbook, okay? So if we're gonna do the string, and we're gonna do the string, waves traveling on a rope, basically, we're gonna see this equation at some point pop up. All we do is apply f equals to ma. Then all of a sudden it's going to pop up. So instead of solving it and going through the solution, which we don't even know how to do, honestly, for partial differential equations. This is a partial differential equation, basically of the second order, okay? So, and leave that discussion to when you guys take DFQ later on. We're going to just reach this point when we apply f equals to ma and say, you know what? I know specifically what that is. That is a wave, similar to everything that I was showing earlier in GeoGebra. That exhibits interference, does this, and so on and so forth, okay? And then, if it doesn't show up to be like this, then we have, we say, okay, this is something else. It's not a wave. This is the wave. This is exactly what we're looking for. The same thing when you guys did also this one in physics 4A, you looked at this equation and you saw it pop up, whether you're doing a mass spring system, whether you're doing an oscillation on the string, basically going back and forth, or doing, what did you do in there? I think that's the two main examples that you, also the torsional wave too. So basically you take a string and you basically wrap it around basically, and you let go of it, so it's going to oscillate. So there is a torsional, which is just turned out to be basically the restoring torque, in this case, the restoring torque parameter, which was, I think, at least in some other classes, I use the symbol kappa divided by the moment of inertia of the object that is basically being oscillating in this case, okay? So that is actually similar. So once you reach this equation, you say, you know what? I have a wave. I'm sorry, I have an oscillation. This is the same token now that we're going to prepare for the next discussion, which is on Tuesday, where we're actually going to take a string. So we still have about 15 minutes. So actually we can set up the problem right now before then, okay? I know that I promise usually to do problems, and at least I have 2 problems for you guys. Hopefully by Tuesday we'll do them. And then before we move into chapter 16 will deal actually with sound. And we'll introduce the concept of beats again. We're going to get into the beats there in more detail, and we're going to get into the Doppler effect. And we also probably, depending on how time will allow it or not, we're going to derive the wave equation also for sound and see that it fulfills this very same promise too. Okay, and as a matter of fact, for those sitting in Physics 4B toward chapter 32, we're going to see this wave equation again there too. So when you see it, you recognize it and you say, you know what, this is a wave. Okay. So I know it's in the book, and I know you're not familiar with partials yet, at least from your calc classes. I hope this was a brief introduction to it to help you reach that point. So when we're dealing with the string, we have no problem with it. Any questions about this? I think we need to change the symbols in here. I think probably because the topic is so hard in here that sometimes it's better to stick with the notations, because the letter U and W, they're actually easily used in here in contrast to X and T, which are the space and time parameters. And this usually use them in calculus to do variable changes and things like that. Okay, so we have so far 2 items of discussion. Hopefully you picked up on them. The section, we still have about less than 15 minutes, actually about 10 minutes. So here is the situation. So what we're doing now, we have a string now, okay? Let's say it's fixed from one side and you create a disturbance in it. Okay, so the disturbance will travel in the string, reach the other side of the string, and probably bounce back, and so on and so forth. So that's basically what you can do. It doesn't have to be really fixed on the other side. It could be open too. So it could go like this, swing up and come down. Basically, as it's coming down, it's creating a disturbance in the opposite direction, and so on and so forth. Okay, so that is one thing that waves do. As a matter of fact, waves reflect. Okay, once they meet a separation between 2 different media, they bounce back, and you can see that actually on the surface of the water. As the surface of the surface wave hits the edge of the water, it's going to come back, maybe with less intensity because again of losing energy, but that's another issue. Okay, so that is again some of the behavior of waves. So we're going to study reflection and refraction far more in depth when we do optics. But this is actually a characteristic of wave. It has nothing to do with anything else at this point, okay? So we have a string. I'm going to assume the string is long enough for me to take a part of the string. So this is not the whole string. This is just of the string that was initially sitting vertically. So this is the string initially. So this is a point X in the string, and this is a point X plus delta X in the string, okay? So this is the x-axis, and this is the y-axis, okay? So this is not the whole string. The string extends, okay? So there is portions in here I'm not drawing, and there is portion in here that is not drawing. I just took a portion of the string that is located between the points x and delta x. As a matter of fact, you know what to expect from calculus. This delta x will go to 0 at some point. You know that. I mean, we're going to push this to 0 so that we're dealing actually with a small portion of the string. So I'm blowing it in here so that you guys see how it looks like, okay? Now, I'm going to assume that this string has a linear mass in mu. That means that mu, if I take the entire length of the string, mu is equal to the mass of the string divided by the length of the string. So if that string is 1 meter long, and this is what we do in the lab when we do standing waves, by the way, we take 1 meter long of the string and weigh it and then put it in, and then that is my mu. So the unit for mu in here from the up front is a kilogram per meter. So this is a linear mass per unit length. In other words, I didn't take the entire string, I took just delta x portion of it. This has a mass that is a mu delta x. So this is the mass of the portion delta x of the string. Okay? The string was vertical. Again, it was undisturbed. The minute I created disturbance in it, part of the string will go up and part of the string will go down, and this disturbance will travel. So the way I'm tapping this wave is by this function y, which is really a function of both x and t. X is along the string and t is the time, because in any given point, that point can go up and down. Does this make sense, the setup of the problem?
Yeah.
So this is waves on a string. Okay, that's what we're trying to study. The string has a tension T. That's what keeps it straight, by the way. If you cut the string to cancel the tension, the string is no longer straight. So you need tension to keep it in its location, to keep it this way. So this is before, okay? But now the string is in this position. So this is this portion of this tension, and this is this portion of the tension, okay? Yes?
Yes.
So that's what keeps it actually from falling. Let me redraw now the picture since we set up the problem. So let me redraw it. So this is points in space, and this is the portion that I'm talking about. Obviously, this delta x is small, but I'm just taking a big microscope and basically looking at that one as big as I can to see what's going on. So this side in here, I have this tension, which I'm going to call it F. And on this side of the tension, I'm going to call it F. The F is the same in here in magnitude. Okay, but it's tilted, as you can clearly see in here. This is at position X, and again, this is at position X plus delta X. The way this is tilted, by the way, this is delta Y. This is the disturbance in here in the Y direction, because this portion of the string is small, so this is how much it went up, okay? This is the angle with which it's tilted. This is the same angle with which it's tilted. I'm assuming that this portion is small enough so that I can assume it's straight line, okay? So this is more or less straight. I know it's curved a little bit in the picture. So this is actually the same angle theta. As you can clearly see, the tangent of theta is equal to delta y over delta x from the geometry, okay? Theta is actually the slope, or tangent theta is actually the slope of the string itself, how tilted it is, okay? So I'm going to, which law do you think I should invoke now? I have the forces. This is some sort of a body diagram, free body diagram, because I cut the rest of the string, I replaced it by its tensions. So now what force, what law should I invoke? Which law? We have the forces, and now we're ready to do what law to find the, from physics 4a? Which law do you know from physics 4a?
Talk about Newton's law?
That's the only one we know. Is there anything else we know? I don't know any other law at this point, okay? Does everybody agree with Lawrence?
Which Newton's law?
Second one. That
Oh,
is the
yeah.
that is the okay. So we're gonna say F equals to MA. F in general equals to MA. Okay. I have two forces now on this portion. First of all, the mass. The mass is mu times delta x. Because I took a delta x element in here whose linear mass is mu, therefore I have this much mass in it. Times the acceleration. The acceleration is the derivative of y with respect to t. Twice the second derivative. So this is my acceleration. And I have to use the symbol in here, partial, because I know, as I said before, that this function y depends both on location and space. So I have to use these partials in here. So this is my F equals to ma. This is A, this is M, okay? Now I need to find the forces on the other side. This string has this component. Let me use a different pattern here of the force. This force is this component in the y direction. The x direction, I'm going to assume that string is not moving back and forth, so they should cancel, okay? It's the y component that is of interest to me in here. So, and this is the component of this force that I am interested in, okay? It's this component, really. Obviously, as you can clearly see, this is the opposite to theta, so I'm dealing with the sine of theta. This is the opposite of theta, so I'm dealing with the sine of theta. This is negative, that is positive. So I'm going to take that into account. So I have on one side F times sine of theta in the direction where we are in x plus delta x, minus F in the side where we are in x. That's the only difference I have in here in mind. You guys see that? Sine of theta evaluated to two different locations. One of them is on one side, the other one on the other side. I'm going to make an approximation in here. Small waves, just like when we did small oscillation when we were doing the pendulum. Small disturbances require that theta is roughly equal to sine theta, which is roughly equal to tangent theta. Again, because of the fact that tangent theta is actually equal to sine over cosine. And cosine theta, when theta is small, is 1. So sine theta and cosine theta are equal to 1. As a matter of fact, if you guys did the Taylor series, for sine theta is equal to theta minus theta cubed over 3 factorial, whereas plus some theta cubed, theta to the power 5 over 5 factorial and so on and so forth. So plus negligible terms of the order of theta squared, actually theta cubed, okay? Because I included the first leading term in the Taylor series. Whereas cosine theta is going to be 1 minus theta squared over 2 factorial plus the next term is going to be theta to the power 4 over 4 factorial and so on and so forth. So terms of the order of theta cubed, again, I'm neglecting them, okay? So this, when theta is very small in radians though, sine theta is actually equal to theta because this is negligible, and cosine theta is equal to 1 because this is negligible, and tangent theta is just going to be theta over 1, which is just sine theta. Does this make sense from your Taylor class? Did you guys do this stuff in already in math or not?
Yeah, I remember this.
Yeah.
Okay. Sine theta, I'm going to replace it by tangent theta then because of this approximation, because we're doing the small disturbances. So what I have in this case is F, open parentheses, tangent of theta, evaluated at the end of x plus delta x, minus tangent of theta, evaluated at the point x, is equal to ma, which is mu times delta x, times the acceleration, which is in this case the partial of y with respect to t, okay? Where tangent of theta with respect to x is just the ratio of delta y over delta x, because this is delta x. Tangent of theta is delta y over delta x, that's all. And in the limit when delta x is small, delta y over delta x will reach actually dy with respect to x. That's all. So what I'm looking at in here is this one, is f times the partial of y with respect to x evaluated at the point x plus delta x, minus the partial of y with respect to x evaluated at the point x is equal to mu times delta x times the partial of y with respect to t. We still have 1 minute, so let's finish this thought in here before we go home. I mean, I know we are home already. So what I'm going to do is divide by f or I'm sorry, divide by mu delta x. So I'm going to have in here f over mu times this partial of y with respect to x evaluated at x plus delta x minus the partial of y with respect to x evaluated at x divided by delta x. The whole thing is equal to the partial of y with respect to t. I divided by this parameter. And the limit when delta x is equal to 0, goes to 0, I'm sorry. This difference will just becomes the difference between two functions evaluated at x plus delta x and x. Remember, this is a function of x and t also, and this is a function of x of t. So what I have in here, I have is this situation. I am back into this situation in here. The partial, as the derivative of, I'm changing x from location x plus delta x and x. T can be the same point. Actually, it's the same point. When the limit when delta x goes to 0, this is actually the derivative of whatever is in the numerator, which is already a derivative by itself. So this is the derivative of the derivative. So this is actually the second derivative. So what I have in here, I'm going to write this one first. I have the partial of y with respect to time is equal to f over mu times the second derivative of y with respect to x. And this is exactly the wave equation. This is really that same thing I have written before. This is this equation, okay? Well, except that I didn't move the v squared to the other side, where v now, the velocity of the wave, is going to be equal to the square root of the tension over the linear mass. So we were able to find a wave equation using Newton's law, and not only that, we found actually the velocity with which the wave travels on a string. It's a minute past the due time. I know that probably you have other classes. When we come next time, we're going to pick up the discussion from here. Okay, we're going to do the harmonic wave. We're going to do some problems, and we're going to move on to the next chapter after that. Okay, does this sound like it's a good plan?
Awesome. Yes.
Sounds
Okay.
good.
Okay, see you guys Tuesday.
Alrighty.
So-
Thank you.
See you later in the day, okay?
Yeah.
Later.
See you.
Okay, bye.
Bye.